Hi there, welcome back to Tea and Code. Today we're going to be solving Koko eating bananas problem. The brute force runtime for this problem is n squared, O of n squared. We're going to be using binary search so that our algorithm can compile given the constraints. Anytime our algorithm is going to run at n log k for n elements and k range between the elements. Anytime we see a set of values of ordered values and we need to search this set of ordered values or elements, we should always think of using binary search. I've got with me a cup of chamomile tea. Grab yourself a cup of tea and let's get started. So here's the problem: Koko eating bananas. Koko loves to eat bananas. There are n powers of bananas. The ith power has power I bananas. The guards have gone and will come back in h hours. Koko can decide to eat her bananas per hour eating speed of k. Each hour she chooses some pile of bananas to eat and eat k bananas from that pile. If the pile has less than k bananas, she eats all the bananas instead and will not eat any more bananas during this hour. Koko likes to eat slowly, but she still wants to finish eating all bananas before the guards return. So this is the h time that we were given earlier. So return the minimum integer k such that she can eat all the bananas within h hours. So she has to eat enough bananas from each pile so that she can eat all the bananas per hour, so she can eat all the bananas while remaining under the time limit that we're given here, h time. So you can see here, so 4 is the minimum time, is the minimum amount of bananas per hour she can eat while eating enough bananas before h time. So in the first pile, she eats only 3 bananas, not 4 bananas. That in that hour. In the second pile, she eats and then it's this, and in here she goes twice and we have a remainder of 2. Here she goes twice and she has a remainder of 1 from the third pile, and here she eats 3 times and we have a remainder of 1 from the third time she's ate the bananas. I'm just saying that just to show that she doesn't eat all the bananas from each pile. She may stop at each pile, depending on whether her max pile is the amount of bananas she's going to eat is the amount of bananas that's there. So let's code this. So first of all, we want to pick the maximum element from the array. That way, we will start from the minimum. So we'll start from 1 banana, and we'll go all the way to the maximum amount of bananas to eat in the pile. Because if we straight away choose the maximum amount of bananas, Koko won't be pleased. She wants to eat the bananas slowly, so we want to pick the minimum amount of bananas. However, if we pick 1, we won't have enough hours. We'll spend too many hours eating the bananas. So if we picked 1 here, for example, it will be 1, 3, 6, and already we've gone past the time limit. If we picked 11, Koko won't be pleased because she can have 4 and still be under the 8 hour limit. So first of all, we want the minimum and the maximum possible values, and the minimum value is always going to be 1. The maximum value we can select from the array, so we'll just put it to int max. So here we're just selecting the maximum value. So you want to so she's going to be picking a k number of bananas. We'll start by giving it the max, but we'll try to go towards the minimum value. So we'll start with the maximum value, which is we've already done. And now, if the algorithm that I just described, where we select amount of bananas, we'll run it in n squared time, because we have to go through we have to go from the minimum. We'll run in n times k time, n times k, or n times n, because we have to select a value from. We have to select a number of bananas that we want to eat, and we have to eat, and we have to see how many times we'll be going in each pile in, and so that we can sum up, see if we can eat the enough bananas before h time is up. So that will run at n squared time. But because there's an order to the number of elements that we're going to pick from, so we can go from 1 all the way to 11 in this example. We can pick a value from 1 going all the way up to 11. And yeah, so we can pick that, but Koko won't be able to wants the minimum value, so, and she wants to eat it and eat all the bananas before the guards arrive. So so with this is an n squared algorithm. So I'm just repeating myself here, and it's n squared. So the from the first element all the way to the so from the first value to the last value, from 1 to 11 is an ordered set of numbers. So we can use binary search to make this faster, basically. That's what I'm trying to get at. So we can use binary search to change that time from n linear time to log of n time. So we're going to use binary search here. So here we're going to sum up all the bananas per pile. So for each pile, we're going to choose the amount of bananas we're going to eat for each pile. We're going to eat a certain amount of bananas. So that certain amount of bananas is going to stay constant throughout each pile. And we're going to use the ceiling function as well to get so that we don't eat any more bananas after the bananas have run out. So we stick on in that hour. We stick on that pile. Remember to use the double function here, so that when you do division, so that it can be rounded. Otherwise, it will be integer division, which by default floors it's in the nearest integer. If we reach the end of our loop, that means that the amount of bananas are less than or equal to h. So that means we've eaten enough bananas to finish all the bananas within the time that before the guards come back. So sum is less than h equal to. So in this case, what we want to do is we want to set a new minimum, because Koko likes to eat bananas slowly, so we want to set a new minimum amount of bananas. And also we want to search we want to find an even smaller amount of bananas. So we're going to search, we're going to move the right pointer to mid -1. So move the right pointer from here to there, so that we can search within the lower part of the array to get even smaller amount of bananas. Give us a run. Oh. Okay, submit. So there we have it, guys. If you found this helpful, please let me know in the comments down below. Also, if you want to see more other algorithms or data structure problems, if there's other algorithm problems or data structure problems that you would like to see, please comment down below. Don't forget to share, like, and subscribe to see more content like this. Until next time.